So let me see a show of hands for everyone who owns a camera. Okay, for those who didn't raise your hands, do you own a smartphone? All right, so clearly you have a camera too, right? So in fact, not only do you have a camera, but you have many of them, right? So just looking at my own phone, which is actually pretty old, it has two cameras in the back. It has a camera in the front for selfies. It has like a Face ID for actually figuring out your identity. It also has a proximity sensor, which actually figures out whether you're bringing your phone to your face, and that's actually a camera too. And for newer phones, you have even more cameras in the back. All right. So in fact, cameras have been transformational to the development of AI. And even though most of what you heard today is about sort of the algorithms that can take and sort of analyze data, some of them can be images or videos, what I'm going to focus on here is actually the camera itself, like where cameras came from and what their future might be. And with that, I hope that I interest you a little bit into the field of imaging in ways that it applies to advanced forms of perception. Both 2D perception, 3D perception, and perhaps a lot more. So we're going to be looking at cameras that can do a lot more than what our what our eyes can do. All right. So I'm going to start by saying that, well, it's been almost 10 years now that the speed, memory capacity, and power consumption of our cameras has become good enough to completely blur the distinction between snapping a photo and capturing a short video clip of a special moment. Okay, so with this live photo functionality which already exists, it's much harder to miss a key moment. Okay, because let's say the shutter didn't click at the right moment. Because once we have a video, we can always fast forward or rewind to get exactly the snapshot we want. All right. Now, this live photo functionality was actually predicted almost 20 years ago by two researchers in computer vision who introduced what they called the moment camera. So here's what they said back then. This is 2006, okay? So future cameras would let us capture the moment, not just the instant when the shutter opens, okay? Rather than only record a snapshot, the camera will constantly record time slices of imagery, basically short video clips. All right? But what is a moment? What is an instant? What is a snapshot? Are these terms that we can define any way we want, or are the fundamental constraints coming from physics and electronics that dictate what a camera can do? And more to the point, can we imagine a camera that can record everything that can possibly be recorded? All right? A camera that can capture passively all moments and all possible snapshots, no matter how short or how long they are. All right? So what I'm going to be focusing on for today is to give you a sense of how far, but also how close we might be to this hypothetical camera. Okay? So let's start from the first moment, in particular, the first moments ever recorded. Okay? So this was back in the dawn of photography, in the 1800s, when this famous photographer, Edward Muybridge, was given a very specific problem to tackle. Okay? It was a problem about horses. All right? The question was this: do all four hooves of a horse, are all four hooves of the horse in the air when a horse gallops? Are they ever all in the air at the same time? Okay? This was a problem that, bothered a whole bunch of people back in California those days, and it took him many, many years to figure out a way to conclusively answer this question, okay? And the way he answered it is by developing a camera system that sort of allowed us to capture these moments. So what did they do? What did his camera do? He had an array of cameras side by side, okay? And each one of those cameras had a shutter that was triggered by a tripwire as the horses move across. Okay, so as the horse moved across, these cameras, one after the other, the shutters opened and closed through these tripwires to allow different snapshots, different instants in time to be captured. Okay, so through that, MyBridge was able to again conclusively answer this question. Indeed, horses do have all four hooves in the air at the same time. Okay. And in doing so, in answering this question, he was also able to record the first video clip ever recorded. In fact, these were the first movies ever captured, okay? What you're seeing here. So at a time of photography where photographers typically captured a photo by physically removing the lens cap, allowing the film to be exposed and putting it back on, he was able to record video at effectively 1,000 frames per second. All right? This was in the 1800s. So now I'm going to fast forward about 70 years and show you a short video clip about the state of the art of high-speed imaging at the 1950s, where one of the main subjects of interest was actually filming atomic explosions. So let's hear how they did it.
A special camera called the Rapidtronic was developed at EG&G to photograph the initial burst of energy in the first millionth of a second. 6 cameras simultaneously captured the progression of the fireball as it vaporized the tower. Here, these images are combined to give the impression of motion.
The cameras were mounted on racks up on top of a 300-foot tower in a cab. And so usually in each tower we had 6 cameras. And they were stacked one on top of the other. And this is so precise that we can have 2 cameras sitting side by side or 600 meters apart and have them go off within a millionth of a second of each other.
So this particular system is just like MyBridge's cameras, except with faster electronics. Okay, so they were able to capture individual snapshots, like you see here, where the effective frame rate was about 1 million frames a second. Okay, but here's another property that both MyBridge's camera and these cameras have in common. As we started capturing shorter and shorter frames, we're also recording time spans that become shorter and shorter as well. Okay? So this is an important trade-off, because if we want to capture all possible moments, not just the fastest ones, this form of high-speed imaging is not sufficient. All right? And one way to quantify the performance of video cameras and how they are able to capture both short and fast moments, we can think of something that we could call sort of the temporal dynamic range of a camera. I don't know how many of you have heard of the concept of dynamic range. Maybe raise your hands. Okay, just a few of you. I bet if you go buy a TV today, you're going to find that a lot of them, advertise that they are high dynamic range. What does that mean? Well, in the context of intensity, it means the range of brightness values that a TV can emit or a camera can capture. So you can think of it as a ratio of the brightest intensity to the dimmest possible intensity that a camera can record, for example, if we're talking about cameras. So just like we can talk about dynamic range for intensities, we can think about dynamic range for time as well. So you can think of that as basically the maximum possible duration of a video clip divided by the minimum possible duration of a single frame. All right? So with high-speed imaging, and for those of you who are maybe more mathematically minded, you can think of this as let's say the highest frequency that can possibly be recorded at a given pixel divided by the lowest possible frequency that can be resolved in terms of like a temporal variation. But let's not worry about that. Let's just think about this ratio of maximum duration of a video clip divided by the minimum duration of a frame. So high-speed imaging is really concerned about making those frame times as short as possible. Okay, 1 million of frames a second, 1 billionth of a frame a second. We're going to see that later. But when we're talking about the ultimate video camera, we don't simply want to record short time spans. We want to record everything, both short and long. Okay? That means we want to be able to maintain very, very short, the ability to capture very short spans of time, but also maintain a high temporal dynamic range. So let's see how, and like in this context, both the Muybridge's camera as well as this Rapatronic camera that I showed you from the 50s have a very low dynamic range. It's just, again, the total number of frames that can be captured. In this case, it was, 9. In Muybridge's case, it was about 12. All right? So very, very small dynamic range. So the ultimate video camera is a camera that can passively record any given time span at the maximum possible temporal dynamic range. It can record everything, both fast and slow. All right? And this is going to be the sort of the main subject. Can we do this? How far can we go? Now, how do modern cameras fare if we think about, again, this notion of temporal dynamic range? Well, we have cameras today that you can let them run for years. Right? What you're seeing here is a time lapse over about, 10 years, 8 years at a particular location. All right? So we can certainly record for a very long time, possibly indefinitely, with cameras that we already have. And we also have off-the-shelf cameras that allow us to record all sorts of high-speed phenomena, from falling droplets to lightning, even to speeding bullets. All right? This is something that we can do today with the devices we can practically buy in a store. And so if you think about the maximum possible time span of multiple years that cameras of today can record, and the microsecond time span that some of the fastest high-speed cameras allow us to capture today, we have a temporal dynamic range which is already quite large. Okay, basically it's like saying I'm going to record for 5 years at the temporal resolution of a microsecond. Okay, you get a dynamic range which is 10 to the 14. And even if you consider capturing just a short video clip, 1 second, we can already, using these advanced high-speed cameras of today, capture, videos with a dynamic range on the order of 1 million. But this is nowhere close to the speed at which modern electronics actually work. Okay, so you go to the highest possible digital electronics, they operate at time scales on the order of picoseconds. And even though you may think that, well, given how fast those electronics are, we may be able to record videos that, even for within a time span of a second, we can resolve, events happening over, 12 orders of magnitude. This is actually not the case. All right. So there is, in fact, almost like a brick wall that happens when we go to capturing snapshots of time that are less than about a microsecond. Okay? So what happens at that point? Well, what happens is when we go to these shorter time scales, that's when we go into imaging systems that are actually extremely useful today. These are time-of-flight cameras, depth cameras, systems for ultra-fast biological imaging. All these systems work in a regime where these individual snapshots in time are on the order of nanoseconds or picoseconds. All right? And in those cases, the dynamic range, this temporal, the ability to record both fast and slow events becomes very, very limited. Okay? So it almost is another phase transition of sorts, in the sense that once we go to frames that are about less than a microsecond, there is a very tight relation between the time span of one frame and the time span of the whole video clip that can be recorded. Maybe not more than 1,000, a factor of 1,000. So you can record videos that are about a factor of 1,000 of what an individual frame can give you, all right? So even though it's possible to record shorter and shorter frames that represent shorter and shorter times, the total span of the video recording becomes very short as well. Okay, so this is not unlike the MyBridge camera and the Rapatronic camera that I showed you earlier. Okay, so why does this happen? What is it that causes this big difference in how we do imaging when we go to these short timescales? And the reasons for that actually trace back to techniques that were developed by a person called Doc Edgerton, who was a professor at MIT in the 50s, 40s and 50s, and who in fact was the inventor of the Rapatronic camera, and has also been the father of high-speed imaging. All right? So what are the fundamental constraints that these systems that involve measuring distances today and other kinds of high-speed cameras, what are the constraints that these cameras have? Well, the constraint is that ultra-fast imaging today requires precise synchronization with a single dedicated high-speed light. Okay? So why is that? So let's first consider the question of why do we need a special light when we want to capture very high-speed images? Well, here are the guys who are actually filming that bullet that went through the egg a little while ago, all right? And the interesting thing here is not that the fact that they had this super-duper camera in front of them doing that filming, but the fact that they were doing it in the blazing sun, all right? Because they needed to capture individual frames that were well exposed. They needed enough light to capture a frame that lasts a microsecond. And if you need so much light to capture an image that represents a microsecond in time, well, there is simply no natural source out there that can possibly allow you to capture images that correspond to nanosecond or picosecond time frames. All right? So let me show you another video. This is in fact from the 1940s, where Edgerton himself explains why not only do you need this artificial light to provide enough illumination in the environment, but why this light needs to be super fast as well, okay? And I'm gonna just play you a few clips of this video, but it's actually a very cool video. It actually received an Academy Award back in the 1940s, and it has lots of insights, so I highly recommend it.
Still photographers are very busy these days, snapping pictures of fast-moving objects and whatnot. A fair degree of clarity is attained with the aid of the modern flash bulb attached to the camera. We'll see the results of this later. Edgerton uses the same camera. When it's hooked up to his things and stuff, however, he makes the average action picture look like a broken-down tintype. The high-speed light does it. Each flash of that light lasts 1/30,000th of a second, which is faster than a goose in a high wind. So, we take the picture. Here's that first picture made with the usual flash bulb. Note how the shoe and ball are blurred. And here's the photo by Edgerton, clear as a California morning. Well, some California morning.
All right, so next time you go to a club and see all these flashing lights, okay, think Edgerton, because he was the one who actually invented them. Okay, so let's fast forward 80 years from that, okay, and now we're going to the record holders for high-speed imaging as of, let's say, 2020, which basically use the same idea, only much faster electronics and a much, much faster flash. Okay, so this was a laser that emitted these super fast, super short, but super large pulses. Each pulse corresponds to about 1 billion times brighter than a laser pointer concentrated at a single spot. Okay, so I'm not going to put my hand there to take any photos. It's just way too bright. All right, but this is what they had to do to actually capture snapshots that represented, picosecond timescales. And you can imagine if you need to pack so much energy in this one pulse, you cannot do that very often. it only lasts a very, very short period of time. And that's why you end up with the ability to only record an extremely short fraction of time. So you may be able to get a few snapshots that are, super short, but again, you can't do that for very long. All right? Okay, so how do we capture high-speed images, even at these time scales, without as much light? Well, the answer to this comes from Edgerton again, using the principle of stroboscopy. How many of you here have heard of the term stroboscopy before? Okay, very few, not a problem. Let me show you Edgerton again, explain what that means.
The principle of this high-class gadget is a light that flashes on and off at variable speed. Through this invention, you can examine machinery in motion. Here, a common electric fan is used in a simple demonstration that even I can understand. Or can I? Anyway, when you direct this light on a fan and synchronize the light flashes to the revolutions of the fan, the blades appear to be stationary.
All right, so once you've synchronized them, right, you can just record for as long as you want because you've effectively frozen time. All right? And this exact same principle has been used recently, in the last 10 years or so, to capture videos that are so fast, you even see light in motion. All right? So here is, for example, just a Coke bottle with a laser shooting through it. This actually laser emits individual pulses, which are very, very short, but you don't see the pulses at all. You just see the light, okay? But if we use Edgerton's stroboscopic techniques, we can actually freeze light in action. And what you're seeing here is a pulse as it propagates through the bottle at one particular location. So what have we done here? We've frozen time using very fast electronics, okay, and very fast lights, lasers, basically picosecond lasers. But we can use this basics, this same technique to capture images like this. And in fact, we can change the sync between the laser pulsing and the camera to capture individual snapshots. And this was one of the techniques that was used about 10 years ago to create the first videos where you can actually see how light propagates through everyday environments. All right? So what you're seeing here is literally a video of light in flight, okay, as it propagates through this Coke bottle. Now, this is cool, but there is a catch. And the catch is that with stroboscopic techniques, you can record fast events, you can record fast motions, but you cannot record slow ones. Those get blurred away. All right? Why is that happening? Well, it's happening because this is not a single snapshot. This is actually not a single pulse. This is the integration over many, many hours of millions and millions of individual pulses, all precisely timed in such a way that you're getting the same instant in time, okay, and collect enough light to be able to create this image. Okay? So the catch here is, yes, you can record a video of light propagating through the environment, but you cannot record anything, any event that lasts more than just a small fraction of a nanosecond. Okay? You can record something fast, but you cannot record something slow. All right? And for the same reasons, actually, we don't need to be so dark just yet. So this basically means that, again, we have this tight relation between the frame, the individual frame, and the time span that gets recorded. Okay? And in fact, we can only have one light turned on to be able to do this. Let's see why. Here's Edgerton again.
Anyway, when you direct this light on a fan and synchronize the light flashes to the revolutions of the fan, the blades appear to be stationary. To make sure they aren't, it's better to turn an ordinary light on the fan than to stick a finger into it.
Okay, so once you've turned another light on, the stroboscopic effect goes away, and you cannot use that data anymore. Okay, so that means you have to be very precisely matched between the time scale you want to image and the light that will be emitting, whatever light you need to do the capture. So LiDAR systems, which is the next generation of autonomous driving, basically involves these types of sensors. They are operating in this regime. They allow you to kind of resolve distances or to resolve the arrival of individual photons at a very precise time resolution, but they don't allow you to record video for very long. And the same thing happens for other types of high-speed systems. Again, you have to have this synchronization in order to be able to connect enough light, in order to be able to capture these high-speed phenomena. Okay? So, back to our original question now. Is it in fact possible to capture video that allows us to record events occurring across, many, many orders of magnitude in time? Okay, from seconds to picoseconds, all at the same time with the same imaging system. And the answer is yes, we can, but we have to change the way we think about cameras. So let's just step back a bit and think about how images and videos, in fact, how videos are considered today. So here's a sort of a short video clip. We're looking at a specific pixel here, okay? And if you think about the video at the individual pixel level, you can think of it as basically some sort of a time-varying intensity or color at that particular pixel, right? So what that particular pixel is observing is some variation in brightness or some variation in color or both. And if we want to record, if we want to capture a video, you can think of the video as basically some form of sampling of that signal. We break it down into small pieces, we record the numerical value corresponding to each, and that's our video. And if we want to record a higher speed video, the conventional wisdom goes is, well, we just have to sample more finely, and that solves our problems. But actually it doesn't, okay? It doesn't because light, in fact, doesn't work that way, okay? So we may be thinking about light as propagating, in some continuous fashion, but in reality, light is actually composed of individual photons that are propagating through the environment, and we don't have any control over those. All right. So what the camera actually gets is these individual photons, which arrive stochastically to individual pixels on the camera sensor. Okay. And let me show you this photo. So this is actually a photo captured by a camera whose pixels are sensitive to individual photons. So what you're seeing here is a binary image. And every dot here corresponds to a single photon detected by the camera in the time span of 1 microsecond. So I'm going to say that this is an outdoor photo. Any idea what this photo is of? Anyone? Maybe louder? Oh yes, what do you think this is a photo of? This is a photo of something. What is it? It's an outdoor photo. What's that? Okay, good. Okay, let me play you the video. So this is actually the video of basically, 1 million frame per second video of individual photon detections from this camera. So this is in fact the cityscape of Toronto, the city of Toronto. This is actually the CN Tower right here. Okay, so this happens when you have a really, really bright day. But actually, if it was dark, the only thing that would really change is that the rate of arrivals would be smaller. So you'd basically get a very similar video, but the photons themselves would be arriving at maybe 100,000 times slower. So what does this all tell us? It tells us that, again, individual photons arrive stochastically at our cameras. And it doesn't really matter if our camera costs $1 or, let's say, $1 million. We don't have anything to do with the photons. They're coming in. That's all we have. Okay, we can't do anything about that. So if you think about it in these terms, the most fundamental event that we can talk about when thinking about imaging is really the arrival of a single photon at a single pixel. And if you have, let's say, light sources in the environment that are blinking, or you have, objects moving around, and the brightness arriving, at a single pixel varies over time, what that means is that the rate at which these photons propagate is irregular. Okay? And in fact, the rate at which photons arrive could be much, much slower than the rate at which light sources in the environment actually blink. So if you look at, for example, depth cameras that exist today, LiDAR systems that are used by cars and all sorts of other devices, even our smartphones, what happens is that they have a light source which is blinking like a flash, at rates on the order of megahertz. So maybe a few nanoseconds between individual blinks, but the arrivals of the individual photons happen very, very infrequently relative to that. Okay. And in general, when you have a camera, that's receiving, light from many different sources. Some of them can be onboard sources from your LiDAR system or your depth camera. Others can be just, your room lights or maybe the sun. All of this comes together into your sensor, and again, you have no control over that. So, what is the best that can possibly be expected of a camera to do when we want to record intensity? Well, the best we can hope is not to detect the photons, it's not to count the photons, it's actually to timestamp them. So it's like having an internal clock. The camera has an internal clock, a super accurate clock, and every time a photon arrives, it actually outputs a time, the precise time, potentially at picosecond resolution, that particular photon arrived. Okay? And if you think about it, and this is in some sense the most fundamental notion of a snapshot. It applies to every pixel individually because these photons are coming, completely stochastically at different pixels. And again, if you think about it, this is the only possible form of lossless recording of light. Okay? Once you know the precise timing that every one of these photons arrived, you can play that back later without any loss and use whatever vision algorithms or whatever other techniques you want to use to process that data. Okay? So, in this regime, the intensity coming at a pixel is not an observable quantity. It is some time-varying quantity, which is so-called latent, it's hidden, and the only observations we have are the individual photon arrival timestamps. And then that has to be inferred. This time-varying intensity has to be inferred in some fashion. Okay? So, what is, in some sense, the ultimate camera then? Well, the ultimate camera is a camera that can detect every photon, timestamps it according to a super precise clock that follows the arrow of time, at picosecond resolution potentially, and outputs this individual photon timestamps. Okay? And if you want to think about it more globally from the perspective of a video camera, well, a video camera would have to operate, again, passively. It's just collecting light. It's collecting all these photons at all its pixels. And what it has to output is actually an inferred representation of this time-varying intensity that arrives at the sensor, okay? Whose variations may occur at timescales of seconds down to picoseconds potentially. So how far are we from this sort of ideal today? All right? Well, off-the-shelf signal photon cameras already exist on your phones. So the proximity sensor on most phones, certainly all the Apple phones, actually is a single photon detector. And if you have, let's say, an iPhone that has a LiDAR or a tablet that has a LiDAR camera on it, it also uses a single photon camera and a light source that operates at these picosecond scales, well, nanosecond scales, to be able to measure depth. All right? So these cameras already exist on your devices. Higher-end systems that involve single photon detection already exist. This is a very recently announced camera that costs quite a lot, maybe in the tens of thousands of dollars. But there are also tiny little detectors you can buy from the store for like, $10 that also involve these kinds of single photon detection schemes. And from our perspective, some of the higher-end scientific cameras that exist today, they come into two different types when we're talking about single photon detection. One involves what's called these binary cameras. You can think of it as a video camera that just outputs binary video frames corresponding to individual photon detection. So there, a photon lands at a pixel, and the camera, that particular pixel, will output either a 0 or a 1, and that you can think of that as basically your frame. And that happens synchronously for the whole array, so you basically get an image, And this is actually the kinds of images that I showed you before of the Toronto skyline was with a camera like this, where you can capture about 100,000 frames a second. These are binary frames corresponding to individual photon detections. And you can also think about these as cameras that actually timestamp photons at a resolution of about 10 microseconds, and you get about 100,000 photon detections per pixel maximum. Now, the more advanced versions of these devices actually have been used for LiDAR and these kinds of systems, and there, those operate a bit differently. You have a photon arriving at a single pixel, and then the output is the timestamp. It's a precise timestamp. And then that particular pixel gets deactivated, so it cannot detect any photons for a little bit of time. And then once it gets activated again, it can start sort of detecting, and then the output of the camera is not intensity, but it's actually timestamps, an asynchronous stream of timestamps. And just to give an idea of the kind of numbers here, these systems, they give you about, these are things that we have in the lab, they give about 2 million photons per second can be output. Resolution is on the order of picoseconds, and you know, the dead time, basically the time that it's deactivated, is basically a small fraction of a microsecond. But these are becoming much you know, more advanced now. So you see that the detection rates are improving by orders of magnitude. The accuracy of the systems also improves quite a lot. And now we finally have arrays of these devices too. So not only individual pixels, but arrays of individual pixels that can detect photons. They can output asynchronously the timestamps of the individual photon detections. And really, in all of these devices, the fundamental limitation now is throughput, is how many timestamps, how much data can we pull out of that sensor within a short time span, okay? So, going back to this question, well, we do have you know, sensors that can operate passively. They can detect, well, almost every photon. They can operate with a real-time clock. They can really work at a near picosecond resolution. And most importantly, we now have ways to actually do the inference, which means starting from the timestamps, how do we actually get this time-varying function? And I'm not going to, you know, tell you more about how we do that. These are, you know, recent computational techniques that we've been looking at. I just want to show you what this all means and, like, what can we do if we have this kind of data, all right? So let me show you first an example, which was kind of, let's throw everything at a pixel, and let's see what this pixel can detect. So again, this is an experimental system, so I'm going to have a single pixel detector that it can detect photons and output timestamps. That pixel is actually focused on a spot on this box, all right? And that box is illuminated by a whole bunch of different light sources. There is a light bulb, just a standard light bulb that's kind of above it. We don't see it here. We don't see it here, but it kind of sends some of its light at that spot. We have a laser which hits a little, think of it as a diffuser. It's kind of, it basically takes the light and it kind of spreads it around. So think of this as a flash that just flickers at a rate of 3 megahertz, so 3 million flickers per second. We have another asynchronous laser that operates at a different rate, 40 million flickers per second. And finally, we have a laser projector, which actually, again, sends its light onto a little screen. So it's playing a movie, okay? And the faint glow from that movie ends up hitting that spot. So all we get to see is, all we get to measure is photons from that spot there. Think of, like, you know, in the olden days where you had, like, you know, these TVs, like you had a dark room, you had a TV somewhere, you know, like these old CRT TVs, and, you know, you were looking at the wall and you saw that, like, faint glow on the wall, right? So that's what that detector sees, all right? But all of these light sources are running concurrently. So we collect a whole bunch of photons, in this case a few tens of thousands of them, and so this is now how we can go back and see what it is that that pixel was actually seeing, okay? So here you see a plot of the intensity of that one pixel that was, you know, as it was detected, and you see here the time scale here is about a second. So this is basically a resolution of about 1 kilohertz, 1,000th of a second per sample. And what we're going to be doing is we're going to be zooming in time to see finer and finer scale events. So you see here the refresh rate of the laser projector. It's about 60 hertz. If you zoom in some more, you end up seeing the flicker of the light bulbs on the ceiling. These are typically flickering at a rate that you can't notice with your eyes, but it actually does occur. You zoom in some more, you start seeing some of the impact of the laser projector as it's trying to form that image on the screen. And then start zooming some more. Now we're down to microsecond regimes where we're actually making out the individual pulses of the laser, or this is the slow laser. We can zoom in some more, and now we can actually work out the pulses of both sets of lasers. And we can even zoom even further down to picosecond timescales to resolve the shape of just one pulse of the laser. So we've been able to collect all these photons and go from timescales of seconds all the way down to picoseconds with this one device and just passive imaging. Now this was, and in fact we can do more. I'm not quite sure how much you can see this. You know, maybe this is too dim. Perhaps if you lower the lights a little bit, we may be able to see it a little bit better. We can basically take all that photon data that was captured and figure out what it is that pixel was, what video was actually being played on the you know, by the projector. So again, this is like saying, you know, I'm just looking at the faint glow on the wall and I'm trying to figure out what is it that the video was playing. And if you actually turn all the other lasers off and just leave the projector on, you can actually make out the movie itself. All right. Now, this is a single pixel. What about video? What would video, or from a camera that actually is able to image at all these different time scales simultaneously, what could that give you? So let's see an example of that. Could you please dim the lights? All right, great, thank you. So what I'm going to show you here is video of a scene where we have a fan. Okay, so this fan is just a standard fan. It's being, what you're seeing here is video captured by an iPhone. So that's 240 FPS, slow-mo mode of the iPhone. This fan here is illuminated by a ceiling lamp. It's illuminated by this little laser spot that is just a standard laser pointer. And it's also illuminated by another laser which is flickering at a rate of, I think it was about 20 megahertz. That you don't see on the iPhone, of course, for sure. And what I'm going to show you now is the data that we captured. And you know, I'm going to be playing it back as a video, but this is not a video in the conventional sense. I can play this video back at any frame rate I want. I'm going to start by playing it back. So the video will keep moving forward. I'm going to start from time 0. And what you see up here is the frame rate at which I will be playing that video. So we're going to start by a frame rate of 10 hertz. The fan is moving at, I think, 100 revolutions per minute. So this is going to be totally blurred. You won't be able to see it. And then as time goes on, we're going to be moving to shorter and shorter and shorter time scales. All right? So let's see that. So here time is moving. You don't see anything here. It's too blurry. As we increase the frame rate, we start seeing the fan a little bit. 1,000 frames a second, we get to see it pretty well. 2,000, okay, it slows down. 10,000, it slows down even more. When we go to 100 kilohertz or so, it will slow down even further. But of course, the laser, you don't see it. The pulses are too fast. They're too short. You can't resolve them at these times of frame rates. But we're not limited to this. So now what you're seeing is a video at 200 million frames per second where we can actually resolve the individual pulses. And when we go to 10 billion frames per second, we can actually see that actually has a finite speed and actually moves across the environment. So here at 200 billion frames per second, we can actually see the individual pulse moving. So unlike what I showed you earlier with stroboscopy, where we can measure basically light as it propagates along an environment, but we cannot measure slow motions. Here, we can measure motions that are both slow and fast. So it's up to us basically to control the speed of the video in post-processing. Okay? In fact, we can do all sorts of tricks. So here is an example. Here's kind of a video where I'm just showing you a single laser pulse propagating across the fan. And here we're going to be changing, again, a posteriori, how we play it back so that we can freeze the pulse and we can have the fan moving around, or in fact we can even have them move simultaneously together. So here, both the fan and the pulse of light are moving. This is kind of almost physically impossible, because it'd be almost like saying that the fan is moving at the speed of light, but it's actually possible to do in post-production. In fact, we can do all sorts of other things. Like here is an example of our camera. Here is just a standard environment indoors. And what we're going to be doing is having 3 lasers that are flickering. Again, think of them as flashes that are flashing at their own rate. And a conventional camera might be able to capture an intensity image, like the one you see on the right. But this camera can also capture, resolve these like the wavefronts of these flashes of light as they propagate through the environment. We can even determine their repetition, their actual frequencies of emission. We can even separate these lasers from each other. We can even freeze one of those and see how the other pulses move relative to that one pulse. We can do that, of course, in post-production. So it's full control over what it is that we can achieve in this context. All right. So 84 years out of Edgerton, after Edgerton's initial techniques on stroboscopy, we're kind of still imaging fans. So maybe we haven't progressed as much, but perhaps an important take-home message here is that photons are important in imaging, especially in regimes where you have high speeds or low light. And there are really 2 ways to think about photons. You can either think of it as a very noisy intensity measurement, like a 1 or a 0 from a conventional camera. But if you try to improve that measurement by, let's say, collecting more photons and adding them up, that ends up hurting the ability of the camera to resolve very fine-scale variations. The alternative is to think about the photon as potential evidence for high frequency variation in brightness, and that would dictate actually keeping these timestamps and intact and processing them. And that is a way to maintain the capability to image at all time scales simultaneously. So where is all this going compared to where we are today? Well, we already have, in some sense, a way to bring the dynamic range, the temporal dynamic range of a camera down to the picosecond regime. We can image at all these time scales simultaneously, but we are limited by our ability to detect photons very quickly. And what that means is that, yes, we can record at many different time scales, but we are limited in the duration of the event. It can be, the recording itself cannot be less than about a microsecond right now. So we can resolve variations within that microsecond at all these time scales, but the recording itself must last a sufficient time to record enough photons. And as these devices become faster and the throughputs become better, we will be able to narrow this gap so that we can recover events that happen in very short time frames as well. So again, the main constraint right now, going from a single pixel detector that can output timestamps to arrays, is really the throughput. Okay, and that is a fundamental problem that is of major interest both to us and actually some of the designers of these systems themselves. So the last thing I want to show you on the application side is to show you what can be done today from the computer vision perspective when you use these cameras in real applications, okay? So I'm going to play you a short clip from a company called Ubisoft, which is commercializing the systems that rely on single photon cameras, and just to give you a sense of how much better vision can be when we use them.
Automotive camera shown here. It looks great right now, but let's see what happens when we venture off these well-lit public roads. We can already see the lack of detail in the trees, especially on the edges of the frame which aren't covered by our headlights. What if we head in deeper and shut off our headlights entirely? We can recover a little detail by turning up the gain, but this only helps so much. Now, take a look at what the UV-SEP solution is able to see. The automotive camera can't even resolve the intersection to the right, but it's not a problem for the UV-SEP solution. And watch what happens now when the headlights come on. The image adapts instantaneously and preserves detail in the darkest and brightest regions of the scene. The UV-SEP solution is clearly better here for perception. But what about more common situations like driving through a city at night? Well, let's see another demo. At first glance, these clips may not seem too different, but let's look at some individual freeze frames. Here, the automotive camera blurs the sign beyond recognition, but the UV-SEP solution captures the sign, the bricks, and even the text on the lamppost with perfect clarity. In some frames, signs aren't even visible with the automotive camera. Just imagine if this had been an obstacle or pedestrian. The differences are even more stark when the two results are processed to reconstruct a 3D model of the scene. Here's what happens with the automotive camera. You can see some high-level structure, but not much more. In contrast, the UV-SEP solution offers far more detail, down to the signs, the trees, and even more. This level of precision is highly beneficial for downstream perception tasks. We can also turn the cameras inward. In this slow-motion comparison, the UV-SEP solution makes it far easier to see where the driver's attention is directed. Now, let's take a look at daytime performance.
Okay, so again, what I'd like to emphasize here is that there is a revolution coming on the camera side that involves single photon cameras. Photon timestamping provides unprecedented abilities to resolve timescales both short and fast, and to enhance the capabilities of existing vision systems. And high temporal dynamic range video opens many new avenues for the analysis of dynamic scenes, as well as for time-of-flight imaging, depth sensing, and so forth. So with that, I'd like to thank all the students and collaborators who have been involved in some of the work that I showed you, and I'd be happy to answer any questions. Thanks.
Thanks. First of all, I would like to give some more, if I'm allowed, some more information.
Absolutely.
Last year's Nobel Prize in Physics, it was awarded to 3 people who they using light pulse to capture the movements of the electron, and now we are in position to take pictures in a subatomic way.
Right.
I don't know if this technology has been gone commercial or still in the laboratory. And also, when we use photons, light, to capture, a picture, you need to polarize the light and then to use like a high frequency, low wavelength to get the result.
Right. So in everything that I showed here, there is no polarization, no optics. Just think of it as a conventional camera that uses a special type of sensor. So nothing on the optic side, okay? And the camera is completely agnostic to the light sources. You know, there could be lasers, there could be anything. It doesn't really matter. Going back to your original point, however, indeed, the development of ultra-fast sources is progressing. These have primarily focused on, capturing extremely short-scale events, as you said, like atomic resolution. There is other, earlier attempts that, didn't get that far. But these are, again, for very short time spans. and they are very highly tuned to that particular time scale. The question of how do you go from just that specific form of imaging that requires synchronization and all these super fast sources to a form of imaging where not only can you image that, but maybe you can image, not only the atoms, but maybe the molecules operating in a cell, and at a different time scale, and the biological processes that occur at maybe microsecond or millisecond time scales. That's not clear how to do it yet, and the fundamental constraint is really the limits of electronics here, because we are still bound by the resolution of our clocks, and at least for digital electronics, the clocks now are on the order of picoseconds.
Thanks.
Yeah, maybe you need to. Was it this video? Like the? Okay, so. Um, Maybe you can give me a little bit more information. Like, was it toward the end? Was it here? Street. Okay. Okay. So I should qualify that the company that, I mean, you can't really see the video now, but the company that uses these single photon cameras are still operating under the regime where a photon is really just a 1 or a 0, and in order to capture high quality images, you're kind of integrating a whole bunch of these binary images to get something slightly better. So these cameras are very sensitive, but they do suffer from some form of motion blur artifacts, and because some of these frames are also, they have to be registered every so often to account for motion, there may be motion-related artifacts as well. So, we are hoping that these techniques that kind of do away with these binary representations but go to timestamps may provide better, like a better way to represent this data. But, this is still, I guess, work in progress. Yeah. Right. I mean, of course, anything that has to do with computer vision in low light is going to be important. Like, being able to operate in complete darkness, for example, right? Maybe there's some disaster site, and you want to go into some building and you have no lighting, and you want to be able to, operate safely in such an environment. That's one example. Another one is dealing with very high speed events. You want to record some event, let's say maybe it's an aircraft engine or something, and there could be mechanical failures or all sorts of different failures happening at many different time scales. You may not know exactly, what is the scale of the frequency at which, a vibration becomes catastrophic. By recording kind of everything, you can go back later and figure out, like where does this happen? Same with, biological processes. There is work, for example, there's something called the fluorescent lifetime imaging microscopy, where you kind of look at the decay of, fluorescence at a nanosecond scale for individual molecules. But, the cells, operate at many different time scales, and right now you cannot observe them all. You kind of have to decide a priori, okay, I'm gonna focus on that particular time scale, and that's it. So this potentially opens the way for these kinds of examples as well. But I think for our devices, another dimension to all of this is that we want to be able to use devices that operate with low power. So the LiDAR systems, the time-of-flight cameras in our smartphones and drones and so forth, they actually use energy by emitting light. And the less light you emit, the less power you use. So being able to work with sensors and systems that can operate in extremely low power can also be very beneficial there. And I think there's sort of great opportunities for machine learning here as well, because what happens is that whether it is foundation models or other types of diffusion models and other kinds of representations, what they provide is extremely strong priors, right? So, and what priors can help you with is when you have very poor data. So, how can we go from just a very few, photon detections to capture, to actually infer, what could be a likely image or a likely video sequence. These are the kinds of things that are still open. But there is a lot of work to be done by kind of marrying the field of low-level imaging and higher-level vision. Yeah. Maybe from back there, yes.
Thank you, Professor Kutulakos. Congratulations on an amazing talk. Just a big picture question. I cannot help it but ask it: computer vision versus human vision. What are still the challenges? What computers cannot see, versus the human eye? And also, could you give us an idea on the economics? I mean, how much these beautiful things cost? And I'm sorry, one last one. Are they going to be implemented on the autonomous driving? We see the LiDAR, challenge. Okay, sorry.
Right.
3.
Yeah. So what I can give you my personal thought on actually AI as well, and what are some of the open challenges. I think you may consider open challenges at the level of, okay, can we solve arithmetic? Can we solve calculus? Can we, these are fundamental problems about AI. But there's another aspect of this, which is that, some of these algorithms require, entire power plants to operate. And so the power consumption required to train these models and even to run them is extreme. And so the question of how do you go to systems that can consume very low power and still be capable, that's, I think, a major open question. What was your second question?
Economics, cost.
Yeah, economics. Yeah, you're right. So I mean, so the cameras that we use are range from about $5,000 to $20,000. The ones that we have in the lab. Some of them are given to us for free from researchers who are actually working with the sensors. But these numbers are a bit illusionary, because what happens is that if we're talking about a sensor, the sensor itself, is just a small piece on a large silicon wafer, and doing a one-off run on a wafer to get these sensors can be incredibly expensive. But once this goes to scale, the economics change completely, right? And that's the reason why you have, let's say, a single photon array on the iPhone, which is on the order of maybe 150 by 100 pixels or so. Clearly there, we're talking about a few dollars per item. So the economics have to do with the scale. It has to do with adoption. I mean, certainly we, but others as well, are working on trying to find commercial uses and push that direction. We're not there yet. I think the ability for these technologies to propagate from their initial conception, which is like Siemens manufacturing of single photon detectors in 2008, that propagated into research and imaging about 5 years later. We have these results about 10, 15 years after that. It's probably going to be another 5 to 10 years before you see sort of low-cost devices at that level. But again, these predictions are hard to make simply because the economics can drastically change the landscape.
Thank you.
Other questions? Yeah, right here. Right, well, I mean, the comparison that you saw between like the UBICEPT example and a conventional example suggests that, the cameras of today, like the video cameras that exist on your phones, like the main camera that exists on your phones and the cameras that exist in other like automotive cameras and so forth, what they do is they are not, they record light, they are, let's say, they accumulate photons, and they, at the end of the exposure, they provide an output, okay? But when you have low light, the noise properties of your camera makes it so that you cannot really, be very sensitive to low light. That's one issue. And simultaneously, if you're moving, if the camera is in motion, then you have a lot of blur that occurs. So you cannot afford to integrate light, because all that'll do is just create a big smudge, and you won't get a clear image of anything. And that's some of the examples that UBICEP showed. Now, what you didn't see is what's happening behind the hood. And what's happening behind the hood is that this camera is actually recording videos like the ones that the binary videos that I showed you before. So it is sensitive to individual photons, and then it becomes the question of how do you take these binary video frames and create images that are both clear, they're blur-free, and they can be used as input to a vision algorithm. So we are still at the stage where you cannot kind of train an algorithm end-to-end from binary photon data to whatever, like, detector output you want, or navigation system. We still have these conventional images as an intermediate step, and that's why you see these examples here.
Okay, so I suppose the specifics of how UBICEP works are proprietary, or are there insights?
No, these are, of course there's proprietary technology involved, but there is a growing sub-area of computer vision, I would say, that grew from around 2016 to now, called single photon imaging, where a lot of these algorithms are developed and published. So if you go to your, International Conference on Computer Vision and Pattern Recognition Conference, so the main computer vision conferences are the ones where a lot of this work is published, with these foundation models and everything else that is like a bigger part of computer vision today. But nevertheless, the potential utility of these methods is recognized within computer vision, and more people are looking into it, especially as these devices become more common.
Okay, thank you.
Yes. Hi.
Can you hear me? Yeah.
Yep.
I'm a student at the Naval Engineering School of NDUA, and I wanted to ask you, if you think this technology can be used in ship navigation in order to enhance the ship's vision in the bridge of the ship, especially when it's operating in the dark, in order to avoid accidents.
Well, there are two aspects of this. Certainly one is on the ship. In fact, the Canon camera I showed you is like a 3-megapixel camera that was just released this year, and one of the key applications was for imaging on floating oil platforms. So it's more or less the same kinds of conditions that you're considering. There's another aspect of this which is underwater imaging, okay, where you may want to have communication of some kind underwater. Of course, in those cases, there is a vast reduction in intensity, brightness, as you consider larger distances. So high sensitivity does become important. There's definitely applications for what's called computer vision in bad weather, using these kinds of techniques, because in some sense you want to be as fast as possible under your conditions. And what happens in these cases is that these are conditions where they are photon limited. That is, things may be happening at a rate which is slower than the rate at which photons arrive. And so you cannot integrate anymore. So, those are cases that indeed are quite important. In fact, we're talking to ONR, which is the Office of Naval Research, for looking at problems in that space. Any other questions? Up there, yeah.
Thank you. Why we cannot capture videos in picoseconds? Because ideally we could not merge, for example, the frames to create the videos.
So the problem is when you're looking at a picosecond time scale, think about it the following way. Things are happening at picosecond time scales, but photons are arriving at millisecond time or microsecond time scales. So what are you going to average? There is nothing to average.
Yeah, but we cannot merge the results. In fact,
again, the problem is to form an image, you need to collect enough light. The way to collect that light, you need many photons. The photons are not arriving that quickly, so you have to be able to collect photons over extended periods. How can you do that? Well, Edgerton does that stroboscopically, right? So you're synchronizing things, and because you're synchronizing things, you can wait for as long as you need, right? That's kind of the short story of what was done. And in that case, yeah, indeed, you can wait. That limits you to imaging at a very specific regime. If you want to image at a broader regime, then all you have is the time of arrival. And those times of arrivals of the photons at this absolute time where time runs forward, that's really the only thing you have to go with in that case.
Okay, thank you.
Any other questions? Great, thanks. Oh, yes. Yeah. Right, so indeed, one way to think about this is that we would like to be able to use as few photons as possible to form images or videos, right? Oh, yeah, so, well, okay. There's a whole field of super resolution where you actually, in fact, most of the diffusion models today, they actually, create a very low resolution image and then they upsample that using, priors diffusion and so forth. You can certainly do that. There's an element of hallucination there, so then it becomes a question of to what extent do you want to trust a high resolution component of your data? There is an alternative to this, which is you actually use a high-res sensor, but you try to somehow limit the bandwidth required. So rather than detecting all photons or detecting photons from all the pixels all the time, you kind of adaptively figure out, where stuff is happening, and then only output, those photons. And then you don't have to deal with the whole array. So that's more on the question of how do you do adaptive imaging? How do you bring computation really closer to the sensor? In some sense, actually even with conventional cameras, an important component that involves, again, low power sensing is to bring the computation as close to the sensor as possible, even on a second wafer of the same, device, because that's, you reduce communication bandwidth, you have very local computation. Ultimately, that's where things are going. There was a question about how do we, what about human vision? Well, our brain consumes, a watt or something. It's something on that order compared to the megawatts that you need with today's system. So in that sense, there is a huge way to go before we can really talk about systems that are not only intelligent, but they actually have capabilities and consume power equivalent to a biological organism. I think that is science fiction. at the moment. Yeah. Thanks.